In the previous video, we learned about how we can take complex numbers and write them in what we call their polar form. Now, writing them in their polar form is a really nice thing because it allows us to do things like multiplying and dividing complex numbers in a much easier way. Now, it turns out that it also makes the process of raising complex numbers to powers and taking the roots of complex numbers much easier as well. All right, so let's take a look here at example number 1. So we're being asked here to raise this complex number to the 7th power. And so what we're going to do first is put it into its polar form. All right, so what we remember is that if we have a plus bi, then we can write that in this polar form here, and we recall that the relationship here is that r is the square root of a squared plus b squared, and this should remind us, right, of the fact that the x squared plus y squared of a point on a circle is going to give us the radius squared. So take the square root, and that's our r value. And then we know that the tangent of theta is b over a. So we learned all that in the last video. So let's go ahead and do that to this particular complex number. So first of all, we know that our r value is the square root of negative square root of 3 squared plus 1 squared. So r is the square root of, this is going to be 3 plus 1, so the square root of 4. So r is 2. And then, of course, tangent of theta, that's going to equal 1 over the square root of 3. And so in this particular case, those numbers, 1 and root 3, should ring a bell. That should make us think of our special values of 1/2 and negative root 3 over 2 that go together. And then remember, it matters that the negative is with this root 3 on the bottom, right? So that means the negative's with the a, which in the real complex plane, in the complex plane, that first one here, the real part, that's going with the real axis, which is the x-axis. So if I have a negative x and a positive y, we would think of that as quadrant 2. And so what we have to think about here is, okay, what angle would do this in quadrant 2? Well, that's going to be where the x is long and negative, and the y is shorter at 1/2, and so that's going to be at 5 pi over 6. So theta is 5 pi over 6. All right, so now what we can do is we can say that negative root 3 plus I to the 7th is the same as taking r, which is 2, times e to the 5 pi over 6i to the 7th. But here's the thing. We have some nice exponent laws that we remember. So remember, if we're taking x times y to the n, the product of two things both to the n, you can take them separately to that power. So that means up here, I'm multiplying 2 by this exponential, so I can separately say this is 2 to the 7th and e to the 5 pi over 6i to the 7th. And then we also remind ourselves that if I have a power raised to a power, all I'm going to do is multiply those exponents. So I can calculate 2 to the 7th. 2 to the 7th is 128. But now I'm going to go ahead and take e to the 5 pi over 6 I times 7. So that gives me 128 e to the 35 pi over 6 I. And so that is going to be my complex number in polar form answer to this original problem. Now, it would be nice to go ahead and put it back in the form a plus bi, and in fact, they tell us to right here. So a couple things we want to do. First of all, 35 pi over 6, that is an angle we can probably express in a slightly different way. So if we think way back to earlier in the quarter when we were talking about coterminal angles, right? If I subtract multiples of 2 pi from this angle, I'll end up in the same place on the circle. So I might start by saying, okay, this is 35 over 6. And so when we take 35 over 6, that should give us, I think, 5.83. So we get 5.83. So what that means is, remember, I want to subtract an even number of pi's from this value. So what I can do is say, let's take 35 pi over 6 minus 4 pi, which is 35 pi over 6 minus, and then we're going to have 24 pi over 6, which gives us 11 pi over 6. So that means that this polar form here I could also express as 128e to the 11 pi over 6i, which is great. Because now I can rewrite this thing, right? And let's remember up here that this thing, where did that come from again? That came from this formula here, and we didn't really explain how we transferred to this form, but we gave this as a given that these are equivalent. So now I can go back and say this is 128 cosine 11 pi over 6 plus 128 sine, oops, I forgot my I sine 11 pi over 6. And that's something that we know, right? We know the cosine of 11 pi over 6 and the sine 11 pi over 6. Sorry, I'm going to erase my exponential rule reminders here to give myself some room. So we have 128, well, the cosine of 11 pi over 6, right? 11 pi over 6 is right over here. So the cosine is the square root of 3 over 2 plus 128 times I times the sine of 11 pi over 6 is negative 1/2. And then to clean this up a bit, this would be 64 square root of 3 minus 64i. So that is the complex number that you get when you raise this original complex number to the 7th power. In this next example, we're going to take a look at a root of a complex number. So we've got the complex number 4i, and we want to take the square root of it. Now, first of all, let's remember that if we take something like 4i and take its square root, that's the same thing as 4i raised to the 1/2 power. So you can see how if we can just write 4i in its polar form, then we'll be able to apply the same logic that we did in the previous problem when we were raising that number to the 7th power. All right, so 4i, let's not forget that 4i is the same as 0 plus 4i. So that means that our r value is just going to be 4, right? Because we have 0 squared plus 4 squared. It's going to equal 4. And then we're going to have the tangent of theta is equal to 4 over 0. Okay, but of course, where does that happen, right? What are we saying? We're saying that we have this positive y value, right? Positive y, right? And 0 for x. So that happens at theta equals pi over 2. So this thing can be written as 4e to the pi over 2i raised to the 1/2. And then we just apply the same rules we did as in the last problem. And of course, 4 to the 1/2 is just the square root of 4, so that's 2. And then e to the pi over 2i times 1/2. So 2e to the pi over 4i. Okay, so again, we can turn this into its form of 2 cosine pi over 4 plus 2i sine pi over 4. But those are values that we know, right? 2 times cosine of pi over 4 is the square root of 2 over 2 plus 2i, again, square root of 2 over 2. So my answer here, after a little bit of canceling, is going to be square root of 2 plus I square root of 2. All right, so that's me taking the root of that complex number. All right, now on this next page here, we're just summarizing up here at the top with what we call de Moivre's theorem. We're summarizing what we just did in those previous two problems. So in some ways, the way I'm talking about this is a little bit unfortunate. So this, kind of goes back with examples 1 and 2, right? And it's saying just what we talked about, but it's expressing it in the form where we have cosine and sine. But you can see why this is true because when we put it in that polar form where we have it with the exponential e to the I theta times r, raise that to the nth power, you just end up raising r to the nth power, and you just end up multiplying your angle, right, by whatever that power happens to be. That's what happened in both of those examples. All right, now we're going to kind of stay with this idea here in example 3, but we're going to just present the problem a little bit differently. So we're being asked to solve the equation z cubed equals 27. Now, you can probably tell me one of the solutions to this problem right off the bat. Right, z cubed equals 27. It sure seems like z equals 3 should be an answer, right? And it is. But one thing I want you to remember is think back to Math 141. In Math 141, you worked with finding the roots of polynomials. And one of the things that you learned is that you could look at the degree of that polynomial, right, which is just the highest power that appears in that polynomial. In this case, the degree is 3. And that degree will match up with the number of roots that that particular equation has, or that particular polynomial has. And so when I would see, if I saw something like z cubed, and maybe to put it more like it would look in Math 141, so it'd be z cubed minus 27 is the polynomial, and we want to know when is that equal to 0. Well, the fact that the highest power is 3 tells me there's actually 3 solutions. Now, some of those solutions might be complex solutions, right? They weren't all real solutions, but there were always going to be 3. So in this case here, yes, z equals 3 is a solution, but we're kind of expecting there to be 3. So we're going to talk about how this idea of rewriting a complex number in its polar form will help us figure out what those 3 different solutions are. Okay, so I know it's z equals 3, but let's just set that aside for a second and see if we can come up with 3 and the other solutions kind of from scratch. So here's what we know, right? We've got z cubed equals 27. And we know that the way that we're going to end up solving this is by raising 27 to the 1/3 power. Okay? So what I suggest is let's think about how do I write the number 27 in its polar form. Okay, well, 27 is the same as 27 plus 0i. So when I think about the r value, that's going to be the square root of 27 squared plus 0 squared, which is of course 27. Okay, no big surprise there. But what about the angle? So the tangent of theta is going to be 0 over 27. And so from there, we can make a couple observations. I think on the one hand, we can say theta could equal 0. All right. We could also say theta is equal to 2 pi, because that would be the same exact location on the circle, right? We could also say theta equals 4 pi. And then let's go one more. Let's say theta equals 6 pi. Okay? So any of those angles would give me the number 27, right? If I plug them into that polar form equation or formula. All right? So let's just see what happens when we do use each of those angles. Okay? So we'll say this. So first of all, when I use theta equals 0, then here is my polar form of that number. When I use theta equals 2 pi, then it looks like that. 4 pi and 6 pi. Right? You might look at this and say, well, boy, this is just a lot of different ways of writing the same thing. But it turns out this is the key to finding all the solutions, all the complex solutions to this original equation up here. So what do we know? If I want to figure out what z is, I'm going to take this raised to the 1/3 power, excuse me. So that's what I'm going to do. So we're going to take 27 e to the I times 0 raised to the 1/3. So that's going to give me 27 to the 1/3 e to the I times 0 times 1/3. But of course that's just going to be e to the 0, right? And so all I get here is 27 to the 1/3, which is going to be 3, right? And this is of course equal to 1, so the answer is 3. Okay? But let's see what happens if I do it to this version of 27. So if I say 27 e to the I times 2 pi raised to the 1/3, then that's going to be 27 to the 1/3 e to the I times 2 pi over 3, right? And that's going to be 3 cosine of 2 pi over 3 plus 3i sine of 2 pi over 3. And those are special values, and so I can go ahead and say that's going to be -1/2, and this is going to be square root of 3 over 2. So here I get this answer of negative 3/2 plus I 3 roots of 3 over 2. So a completely different solution based on using that version of 27. All right. Getting a lot of stuff in a little bit of space here, so let me change colors. So here, same thing, let's do this. 27 e to the I times 4 pi raised to the 1/3. Well, that's going to be 27 to the 1/3 e to the I times 4 pi over 3. And I'm really running out of space here. That's okay though. Let's just do this. Actually, let's continue right here. 3 cosine, we'll make room for this down below. 3 cosine 4 pi over 3 plus 3I sine 4 pi over 3. So that's going to be 3. So cosine of 4 pi over 3 is negative 1/2, just like it was for 2 pi over 3. But the sine of 4 pi over 3 is negative root 3 over 2. So this is going to be negative 3/2 minus I 3 roots of 3 over 2. So we have these 3 unique solutions here. Okay. So you might wonder, okay, well, what happens when I use theta equals 6 pi? So let's give that a try. So we'll just go ahead and take that and draw a line down here since I didn't do a very good job of thinking ahead. So here we'll have 27 e to the I times 6 pi raised to the 1/3. So that's 27 to the 1/3 e to the I times 6 pi times 1/3. But of course that gives me e to the I times 2 pi. But if I then go ahead and turn that into this version, 3 cosine 2 pi plus 3I sine 2 pi. Well, the sine of 2 pi is 0, the cosine of 2 pi is 1. Guess what? We're back to 3. So we're back to this solution again. So what happens here is that whenever you are solving, and let me go back up to the top, whenever you are solving an equation like this, and you see whatever power you have here, then you want to express your the number that you're going to raise to your fractional power in a number of different ways. How many ways? In this case, 3. Whatever the power is, that's how many different versions you're going to draw. So I didn't need to do this 6 pi because that's my 4th version, and that's just going to bring me back to where I started again. So I see that cube and I do 3 versions and I raise those to the 1/3, and that will give me all my solutions. So if this were z to the 5th equals a number, then I would write 5 different versions and raise those to the 1/5. All right, and then just to kind of wrap this up here, here's what we're saying. We're saying that these different solutions, right, they're all complex numbers. So what we can do is we can think of them as being in particular places in the complex plane. And I'm going to make a circle here. And the interesting thing is, while these are all in different locations, they're all in the same circle. Okay, so of course 3 is right here. But then this one, negative 3 halves, and then 3 root 3 over 2. So that's going to be right here at 2 pi over 3. And this one's going to be down at 4 pi over 3. And so they're equidistant apart from one another. That's kind of interesting. But they're all on the same circle. They're all on the circle of radius 3, since 27 to the 1/3 is equal to 3.